Hello, my name is Cole Brabik. I work in the Hodge and Miri Lab. I'm a Kirk and Marjorie Dawson Family SURF Fellow, and today I'll be presenting on my design for an ultra-fast single-shot timing photonic integrated circuit with data center applications. So as an outline for this presentation, I'll start by introducing the problem, giving an overview of the building block that serves as the core of the photonic integrated circuit, go into the physics of photonic crystals and two-photon absorption, go into the system design of the photonic integrated circuit itself, and then conclude. So to start off, introducing the idea of data centers, which I'm sure is familiar to most of you. Data centers aggregate data from a single location and then distribute it either to consumers within the same location or communicate with data centers in other locations who then distribute it to consumers there. However, data centers are facing a large problem, that being an optical bottleneck. Thanks to Moore's law, increasing transistor density and clock speeds, the data capacity of the electronic interconnects has been growing exponentially. However, bandwidth of optical interconnects, which are used for either long-distance communication between data centers or for longer transmission lines within data centers, have not seen the same level of growth. Fundamental problem here is that photodiodes are slow. The fastest photodiodes seen in commercial platforms are around 25 gigahertz. For instance, that's what you'd see on these Finisar platforms when you account for the bandwidth reduction from interfacing with electronics. By the Shannon-Nyquist theorem, that allows us to have a symbol rate of around 50 gigasamples per second. Additionally, since these channels use quadrature phase shift, each symbol carries 2 bits, so you can say it's about 100 gigabits per second per channel on these commercial devices. However, that's the main problem. In the first part of this decade, we were able to speed up the photodiodes in electronics to get the growth from 40G to 100G, but now subsequent growth has mainly come from increasing the number of channels on these devices. And it comes with an overhead on power and on size, and additionally, each of those channels requires a wavelength individual wavelength, making increasing the growth harder and harder. So what if we take an alternative approach? What if we don't directly characterize the signal, but instead sample it? In such a system, the following system can be used. Sal and Teach provide an excellent illustration. We open a shutter to the slow detector for a small window, allowing the fast signal to pass through that shutter. In that case, the integral of the output of the signal, the output of the photodiode, will then be a sample, or represent a sample of the fast signal. In order to have an array of samples, so we can reconstruct the signal, we simply have an array of these detectors. We have a bank of delays that the signal goes through, and then a gating pulse that allows the delayed version of the sample to each photodetector. The integral of the output of those photodetectors then gives us the samples we want. To physically implement this system, I've developed this device I call a dynamic interference photodetector, which consists of an optical channel with photodiodes along the channel. In this case, the reference serves as the gate, and the physical length serves as the delay. So the physical length the signal has to travel across as it goes along the device. These photodiodes are low absorption as to avoid signal distortion as it travels along the device, and nonlinear to allow the gating effect. We want the photodiodes to only have high responsivity when the reference and the signal intersect. To physically implement this system, I've chosen to implement it on a 2-photon absorption photodiode array on a photonic crystal waveguide. This is used due to high group index, slowing the light, giving more delay for a given length, and the nonlinear photodiode response, which is required for the gating effect. In order to cancel off errors that may appear in the reference from pulse to pulse, we array these photodiodes in the following fashion so that the output is only the output from the signal. Now let's focus in on an individual photodiode. Here's an actual representation of what an individual photodiode would be. A thin sheet of silicon sitting on an oxide, doped as to be a PIN photodiode with a channel that the light can travel along. Now, this kind of structure is a photonic crystal waveguide. It's an array of holes, in this case oxide pillars actually, through the silicon, with a gap in the hole structure that serves as an optical channel. And these devices are very powerful in that they can slow light up to 50-fold when using standard lithography techniques. Now, a formal explanation for how this occurs is that a photonic crystal waveguide offers a periodic dielectric constant. Then by Bloch's theorem, this can be decomposed into band structure with different wave vectors, and then you engineer the device such that the wave vector at the frequency of interest has a very small forward component. An intuitive explanation, however, is the following. Imagine you're running through a furrowed farm field. Your stride can either have your feet land in the divots, slowing you down as you trip, get stuck in mud, or your stride can allow you to land on the peaks, allowing you to move quickly as you go from peak to peak to peak. In a photonic crystal, these furrows and peaks, they represent energy states. The device is engineered so that the wave propagates along the slow propagating energy state. On to two-photon absorption, the process by which this photodiode actually absorbs the photons. In standard silicon, the band gap, the energies of the photons that get absorbed, is too low to allow linear silicon infrared photodiodes to exist. However, two-photon absorption allows nonlinear infrared silicon photodiodes. Two-photon absorption can be imagined as if there was a virtual state in between the ground state and the excited state. In this case, two photons can reach the virtual state and up to the excited state. Now, this is a nonlinear process. It goes as the intensity is squared, so that we have the nonlinear effect that creates the gating. Additionally, however, a small comment is that the two-photon absorption cross-section, represented by sigma TPA in the equation, is usually quite low. But by increasing the intensity by slowing down the light, we can get appreciable two-photon absorption. As for the electrical receiver, it's fairly simple. It's simply a differential charge amplifier, with the output voltage of this device being given by the ratio of the charge to the feedback capacitance. As for combining the electronics and the photonics, we use flip chipping, flipping the electronic chip onto photonics chip to ensure that the interconnect between the two has low capacitance. Now, let's get into the different operating modes of the device. The first is what I call capture mode. In this case, the goal is to characterize a single pulse. The reference is a Gaussian pulse strain with a repetition rate given by the equation, speed of light divided by 2 times the length of photodiode times the group index. In this case, we keep track of the pulse count, n. When the signal pulse arrives, it will generate a signal at the intersection photodiodes. We can calculate precisely where the intersection is by using a simple center of mass equation, weighting each location of the photodiodes by the charge generated by those photodiodes over the total charge generated. In this case, using the reference, repetition rate, the number of reference pulses, and the intersection point, the arrival time of the pulse can be calculated. And this in turn allows for very rapid clock phase detection. As the location of the photodiode, the photodiode where the intersection occurred, immediately gives you the clock phase, not the carry phase, the clock phase. Now this can be captured in nanoseconds, the electronic time, rather than slowly tuning a delayed lock loop on a laser, for instance, to get the clock phase. So this is a very attractive option for clock phase detection. However, what I think is the more interesting operating mode is sampling mode. In this case, we assume that the electronics have a captured reset time t sub r before they can capture the next charge input, and the reference is a Gaussian pulse train with frequency 1 over t sub r. In this case, the signal is any optical signal that you want to sample. The goal is to sample and reconstruct the modulated optical waveform with an array of such devices allowing it to run continuously. So let's walk through this mode of operation. In this case, we're sampling a single sine wave. As the reference sweeps over the single waveform, the signal is sampled. Each photodiode is getting a single snapshot of the signal. This part of the signal to this photodiode, this part of the signal to this photodiode, so on and so forth. And since these signals are much faster than the photodiode's bandwidth, the photodiodes functionally average over that and have a discrete charge that they output. We can then, align the charge generated by each photodiode to the photodiode to get an array of samples. But before we use these samples to reconstruct, we need to consider the nonlinear effects of the sampling. Normally, nonlinearity can pose a problem, increasing the Nyquist frequency you need to sample at. But because this nonlinearity is time invariant and uniquely invertible, it does not increase the Nyquist rate. So we can simply invert the previous equation for the electric field and send the reconstruction filter. In this example, it's a 125 gigahertz sine wave that we've simulated through a full 3D physics simulation of the photonic circuit, then through the electronic circuit, and then sent through a behavioral model for the reconstruction figure. To show its high-speed sampling effect, here we add noise. This is 10 realizations in the presence of the actual noise we see in the simulation. And we can see that even in the presence of noise, it still reconstructs a 200 gigahertz signal with very high precision, which is a much higher sampling rate or much higher frequency sine wave that can be digitized with commercial digitizers. However, to operate, we need to reconstruct it, we need to look at the actual sampling properties. The sampling time is simply given by the speed it takes to cross the photodiode and then the gap between photodiodes. I'll explain the factor of 2. And the sampling frequency is simply given by the inverse sampling time. So why is that factor of 2 there? Well, we can imagine that the factor of 2 wouldn't be there if we were sampling a standing wave sitting on the structure. In that case, you just sample at these 3 points, and the sampling time would simply be the time it takes the light to travel that distance. But when the waves are counter-propagating, what it looks like in the time domain, not the space domain, is that the samples spread out. And they spread out in such a way when the waves are propagating at the same speed but counter-propagating, it basically doubles the speed of the signal. So you get the factor of 2 we saw. Now, to switch from burst digitization to continuous digitization, you simply cascade the devices as shown here. The number of devices you need to cascade is given by the capture and reset time of the electronics divided by the transit time of the light across such a device. Now let's compare this to state-of-the-art high data rates channels systems. Oftentimes these will have tens, if not hundreds of channels in order to allow hundreds or a terabit per second on a single optical channel. With signal optical amplifiers, sometimes maybe MEMS switches. However, this device doesn't require any of those. As a quick run through of the performance of the device, you can calculate that its effective sampling rate of the exemplary device is 500 gigasamples per second, easily increasable to 1 to 2 terasamples a second by decreasing the length of the photodiode, increasing the group index, etc. And comparing this to a commercial optical interconnect, the Finisar 100G interconnect, we can see the max rate per channel is much higher, with the total energy per bit being only 1/3 of the Finisar 100G interconnect. So this device offers many advantages: lower power per sample, it doesn't require MEMS, silicon optical amplifiers, electronic arbiters. It's a fully silicon on insulator compatible photonic integrated circuit. Additionally, the noise frequency and sampling frequency are decoupled. Noise frequency being given by the capture reset time of the electronics, sampling frequency being given by the geometry of the device. Additionally, much higher sampling rate and data rate per channel at a single wavelength. So in conclusion, this device offers a very competitive data rate to commercial optical interconnects while requiring less power per sample. I'd like to give a thank you to the Kirk and Marjorie Dawson family for funding my fellowship, and to Professor Hajimiri and all the members of the Hajimiri Lab, for all of you for watching the presentation. Thank you.